Let's talk about tuning PID controllers. Recall from before that a PID controller is just like the proportional controller we had before with two extra terms, an integral and a derivative term. This means that we have three different values that can be tuned, Kp, Ki, and Kd. So there are many methods of automatically tuning this. PID controllers have been around for about 100 years, so there are many different things that have been done in the past to automatically tune them, but that's beyond the scope of this course. We're going to talk about manually tuning the parameters so that you get a better feel for how PID controllers work. How do you want to do this? We're going to start by increasing Kp until the system oscillates around the desired value. Then you want to increase Ki until steady state error is minimized. And then finally you want to increase Kd until you reduce the overshoot and later oscillations to the point where you're happy with the system. And of course at the end you may want to go back and repeat that cycle to fine tune it, but we won't do that today. Leave that for you for the homework assignment. So what's our example problem? Let's say that you have an autonomous car here. You want to drive it exactly 30 meters to stop at the stop sign. So we have an error here, an error value that will feed into the controller, which is the current distance between the car and the stop sign. And in a perfect world, we drive exactly to the stop sign and stop. It's great. In a less than perfect world, maybe we drive a bit, overshoot the stop sign, go a bit too far, and have to go back. So how do we do this? Well, first off, we've got to ask ourselves, how do we control a car? Well, use the accelerator, the gas pedal, of course. So how do we take the accelerator and turn that into position? How do we model a position? You may recall from a few lectures ago that this equation was on the board. It's the acceleration of an object, a very car-like object, that takes in the control parameters and subtracts off the drag from air resistance and the friction from ground resistance as the car is moving along. So that's going to be our dynamic system equation that we're going to use to control this system. If we integrate that once, we get velocity, and integrate it twice, and we get position. So now we have a dynamic system. Let's go ahead and tune a controller that gets it to a particular position. What does this system look like with no control inputs? That's a question you should ask yourself every time you look at a new dynamic system, so you have an idea of what's happening when you don't give it anything. In this case, it's very boring. If you start at zero position, start at zero velocity, the car is not going to move anywhere unless you tell it to, so that's pretty boring. Now what happens if we give it some initial velocity? So let's say v0 is equal to 20 meters per second. Well, you can see here the red line is velocity at the bottom there. It starts at 20 and goes down linearly to 0. That makes sense. And the position will go from 0 as our initial position up to right about 100 before the car stops, and then it stays stationary. So that makes sense. That checks out. Let's go back to v0 equals 0, and let's try to tune this system so it hits 30 perfectly. So stabbing in the dark, let's try Kp equals 1 first. Get a couple of oscillations here, get a little bit of steady state error at the end, but it's really not so bad. Let's see what happens when we double that. Maybe up is the way to go. Well, it doesn't seem like up is really the way to go. Kp is a little bit too high there. We added another oscillation, and do know that this really is a bit too high even with Kp equals 1 because you're overshooting your stop sign by 20 meters and then swinging back, overshooting it again by 13 or so meters. It's not great to have your car sliding back and forth around the stop sign. Probably not good driving practice. So let's go ahead and reduce it from 1. Let's make it a little bit smaller. Let's make it 0.5. Okay, we got rid of some of those oscillations there. We still have a bit of a steady state error, but we're still going all the way to 50 meters when we really wanted to go to 30. We can probably get a little closer than that even before we consider Kd. So at 0.25, we get a little bit better still. We make it just the one hump there, maybe 45 meters instead of 50. We can still reduce that a little bit further. 0.2, we get that down to 40, and then it stays steady state error about 10 meters away. Let's try just one more step here, 0.15, get a little bit closer still. We end up being about 4 meters away, but you know what, we really want to find the minimum here, so maybe let's look at 0.1. Well, at 0.1 we never actually get to the 30 value here. So if you don't get to your desired value with your Kp, then you're probably not going to get there with Ki or Kd either. So maybe we go back to 0.15 and start tuning Ki and Kd. So let's get rid of that steady state error there. Note that our max error here is maybe about 34 or so, and we're going to try Ki of 0.1 to get this below that. What happens? Oh well, that's not great. System goes totally unstable. Suddenly you're a kilometer away from the stop sign. Probably not what we wanted. So let's try maybe Ki of 0.01 instead of 0.1. That doesn't look too bad. Notice that our maximum error has gotten worse. It was about 34 before. Now it's more like 44. This is something we can tune later. So we're going to call this good enough for Ki for right now and move on to Kd. In a real-world system, you may want to continue improving Ki just a little bit to get rid of some of that, but for the purposes of this lecture, we're good enough. We can move on. So let's start in with Kd and try 0.1. What happens here? Well, we reduce our maximum error a bit, so instead of being about 44 before, now it's more like 38 or so. We're on the right track. Let's try increasing that a little bit more. That's even better. We're back a little bit more like we were after just the proportional. And we do end up staying at steady state of maybe 3 or 4 for a lot further than we want to, but it's still better than it was before. So let's keep increasing Kd. Here we have it to the point where it gets really close to the line, stays pretty stable. We may want to keep this and go back and tune the Ki, but let's increase it one more time and try Kd equals 0.4 instead. So here we end up approaching it from the bottom. We get to within about a meter of the stop sign pretty quickly, and eventually we do actually converge and reduce our error to 0. So that's pretty good. We're going to call this good for the purposes of the lecture. If you had a real autonomous car, you may want to tune it just a little bit more, but this is good enough to give you a feel for what the parameters do. So we ended up finding that Kp equals 0.15, Ki equals 0.01, and Kd equals 0.4. Of course, the values in your homework assignment will differ. It'll be a slightly different problem with the same basic example, but this is what we found for right now. So let's review. You want to start by tuning the proportional gain until it reaches the desired value and begins to oscillate, maybe just before it begins to oscillate if you can find it. Then you want to tune the integral gain to remove the steady state error, and then you want to tune the derivative gain to reduce the overshoot and settling time. And of course, you may want to go back over this and retune all of it to fine tune it at the end, but that's the basic idea of how you tune a PID controller.